right. Good afternoon, everyone. Thank you for joining us for our next exciting lecture in the Fall Design Tech Public Lecture Series. My name is Jenny Sabin. I am a professor of architecture and also design tech and the chair of the Department of Design Tech. And it's my pleasure to welcome Samuel Letter, who is joining us this fall as one of our Design Tech Innovation Fellows. And we'll be teaching a really exciting workshop in the required studio in the first year studio sequence for our inaugural class of design tech students focused on the topic of today's lecture. And I had the pleasure of getting to know Sam last year, basically this time last year, when I was on sabbatical and on a visiting professorship at the University of Stuttgart. And we had a couple of seminars together, and I thought, well, let's see if we can bring him to Cornell. So a bit more about what Sam is up to. He's a researcher in the field of computational design and digital fabrication, and importantly, he investigates the co-design of collective robotic construction systems. He's currently completing his doctoral thesis at the Institute for Computational Design and Construction, or the ICD, which is familiar to many of you, directed by Akam Menges. And that's within the Cluster of Excellence Integrative Computational Design and Construction for Architecture group at the University of Stuttgart. Samuel's work has been published in various academic venues, including Advanced Science, Automation and Construction, Acadia, and ECAD, and exhibited at various venues, including Arts Electronica in Linz, Austria, the Bureau Europa, and Humbase in Stuttgart. He earned his BArch, or his Bachelor's of Design in Architecture, and a BA in the System Science and Engineering from Washington University in St. Louis, so I guess it's welcome home for you, back to the States. And a Master of Science in Architecture through the Integrative Technologies and Architectural Design Research, or what we are familiar with known as ITech program at the University of Stuttgart. And I guess you fell in love with Stuttgart and the programs there and continued with a PhD. So please join me in welcoming Samuel Letter. We're really excited for your lecture.
Hi, everyone. Thanks, Jenny, for the nice introduction. And thanks to everyone for being here. I know with such nice weather, it's maybe hard to come and sit in a lecture hall, but I hope there will be some nice inspiration for those of you who are here in the audience, and also, I guess, thanks for those of you who are online. And maybe to start explaining the title of my lecture, Addressing Architecture and Collective Robotic Construction, I will tell you a little bit about my background. So yes, as Jenny said, I'm a member of the Cluster of Excellence on Integrative Computational Design and Construction for Architecture, otherwise known as the NCDC. And the NCDC is a research cluster that was created in Stuttgart in 2019. And this research cluster is composed of institutes from architecture, different types of engineering, computer science, robotics, the humanities and social sciences across the University of Stuttgart and the Max Planck Institute for Intelligent Systems. And as you might have guessed from the name, the main focus of our cluster is research in the field of architecture and construction. More specifically, we aim to develop fundamental computational methods for integrative design and construction based on continuous and multi-directional feedback in between these different disciplines that are in our cluster. And this we do through the development of computational design and engineering methods, cyber-physical robotic fabrication and construction processes, truly digital material and building systems, and we also aim to reflect on this at the environmental, sociocultural, and ethical levels. And why we do this, I think many of us probably in the audience know that architecture and construction have huge economic, ecological, and socio-cultural relevance for our current society. The United Nations Global Status Report of 2017 states that our entire built world, as we know it right now, needs to be built again in order to meet the demands of rapid urbanization. And if that sounds crazy, it actually is, because our current means of architectural construction are simply not capable of doing this. And one of the major reasons behind this, we postulate in the cluster in Stuttgart, is due to the low digitalization of the construction industry. So what you're seeing on the graph here is actually that construction is by far the lowest as compared to many other industries. And recognizing this gap, we at the Cluster of Excellence are trying to unleash the full potential of digital technologies with our, again, cross-disciplinary research approach. And this includes specific attention to the automation of construction with different types of machines and in different contexts. So I'll just quickly go through to start some of the projects that we're working on. Starting with the largest, we are working on the full automation of tower cranes to realize pick and transportation processes in on-site assembly of multi-story buildings. We are also looking at cyber-physical on-site platforms using a mobile robotic boom manipulator. So what you see on the screen now is exactly that manipulator, which has tracks that it can move around the site and then stabilize itself with those legs. We are also looking at industrial robotic arms, also creating platforms that can be transported in between factory and site for the prefabrication of building components made out of wood and fiber. One step smaller, and a recent acquisition of the cluster are these collaborative robot arms that are on these mobile bases, which researchers are investigating for the automation of indoor construction tasks. And finally, at the smallest end of the spectrum, we are developing custom distributed mobile robotic machines, which can assemble structures that are much larger than the individual machines themselves. And this is known as collective robotic construction, or CRC for shorthand. And this is the automation approach that I've been researching in the past couple of years and will be the focus of the rest of my lecture. So to explain what collective robotic construction is, I generally like to show these two images because they're robots that you might have seen before and are the ones that are of interest to me. And they are mobile machines, which are relatively small, fairly cheap, easily transportable, and can navigate in their own environments. And as the technology for these machines is becoming more advanced, they are beginning to revolutionize our everyday lives, like vacuuming our homes, for example, and not sure how far along this is yet, but maybe in some places actually even delivering some packages. And the collection of these machines into groups is called distributed robotics or multiple robotic systems. There's a couple of names for this, and these systems are teams of mobile robots which solve complex tasks using their shared intelligence. And as compared to other forms of robotic automation, these systems have the potential to do a couple of things. First, boost the overall flexibility in that they can move around, increase fault tolerance, as if one machine breaks, another one can take its place. And as compared to a lot of the other machines that I showed, these tend to be a lot more inexpensive, so generally reduce the cost of the automation system. And because of these advantages, researchers from all over the world have begun to explore how such systems can actually build architectural structures. And this has become known as collective robotic construction. Two examples of which you see on the screen here. The one on the left is actually still being researched at Cornell, here at Cornell. And the image on the right is from a project at the ETH Zurich. And these systems have the potential to break from other construction automation types due to their ability to quickly adapt, respond to different architectural use cases on the fly, and work at potentially unlimited scales. But the area of research is generally quite new and complex due to its inherent interdisciplinarity. Therefore, research today generally leads to the assembly of simple structures, and architecture is seen as an input for the system that's kind of given top-down for the systems just to create. Which leads me actually to my general interest in the field of collective robotic construction, and this broadly fits under the term of architecture, hence again the title of my lecture. But more specifically, I like to break this down into two topics: building systems, and in that I mean the utilization of real building materials and from the construction industry and dealing with the constraints that those materials demand, and on design workflows. And this is about considering how an architect or a designer can be embedded in the overall life cycle of a structure. So this not only includes design, planning, and construction, but also potentially the operation and adaptation of a building. Because these machines are quite small, they can inhabit the structure, giving us the possibility to think about further phases of a building. And these two areas I will cover through 4 projects. Hopefully I managed to get through all of them. And you'll see that each of these two things are touched upon differently in those, under those two topics. So the first I will talk about is the basis of my PhD work, and is now also a project in the NCDC with 2 other institutes, the Max Planck Physical Intelligence Department and the Technical University of Berlin's Learning and Intelligence Lab. And the title of the project is Leveraging the Building Materials Part of the Robotic Kinematic System for Parallel Construction. And so what does that mean? Well, we are using the NCDC approach of co-design in order to co-develop and co-optimize a distributed robotic system for timber construction. More specifically, what that means is we're working on the overall system development, including architectural design ranges, specification for the building material, and construction connection strategies. Developing methods for artifact design using agent-based modeling, and procedures for task and motion planning using logic geometric programming, and on the physical hardware together with a digital twin propagated by visual tracking of the robots and the building material. So the system that we have been developing generally looks like this. It's composed, it's a modular system composed of 2 parts, an active robotic actuator and a passive timber strut. And the robotic actuators alone have very few capabilities, namely rotating, grasping, and lifting, meaning that actually the robots themselves, although they have small motions, can actually not really move on their own. And they must form kinematic chains, as we call them, with the timber struts together in order to give them more degrees of freedom and make them move. And so it's the combination of these interactions that allow for general locomotion, manipulation of the timber struts, and then the eventual construction of timber structures. And these interactions at the very beginning of the project, we kind of collected into some assembly tasks, which you see on the screen here: locomotion, transportation, and dynamic kinematic chaining, which I will quickly describe now. So locomotion involves a kinematic chain composed of 2 robotic actuators and 1 timber strut. It's the action of this kinematic chain being able to walk across a bed of fixed struts. And this is accomplished through the robots doing a series of gripping actions and rotations. And this can also happen across struts with different distances and orientations corresponding to the distance of the robots in a kinematic chain. And also in the vertical plane, which is actually the worst loading condition for the robot. So you can imagine anywhere in between this horizontal and vertical plane, the robots can also operate. dynamic kinematic chaining builds upon locomotion, but was designed in order to express the modular nature of the system. So what you see here is that the first robot rotates the strut, and the second robot can close its top gripper around it, allowing for the topology of the kinematic chains to change throughout the construction process. So this, you might imagine, is good for changing the length in between two robots, or potentially also collecting a robot that's left somewhere on the structure. And the final assembly task is transportation, and this involves the passing and placement of a timber strut. So for this, 4 robots would need to work together, and what you see here is the first one grasp it, pass it to the next one. Further videos of this you will see in the upcoming slides. And if we combine these tasks together, we can consecutively build up struts to form layered structures. And this system we've now tested in the assembly of 2 prototypes at our large-scale construction robotics laboratory just outside of Stuttgart. And what I should say is the coordination of the robots are actually happening through external localization. So what you see in the image on the right is this truss network, and it's a bit hard to see, but maybe you recognize in some of the other images, cameras that are actually used to localize the robots. So this is was the start to the first prototype that we made, which was the assembly of a layer of timber struts on a plate. And this typology is similar to a timber typology that other researchers have been developing in our cluster. The entire construction process looked something like this, with 4 robotic actuators in these 2 kinematic chains, navigating to a location where timber was fed into the system, walking on top of the layer they're building, and passing the strut around the exterior in order to assemble the entire structure. And this was all coordinated through a digital twin that we developed, and it allows us to do a lot of things. So that's design, plan, communicate instructions, and monitor the construction process. And what I want to show in this image is actually what is actually in the center. So the blue represents actually the position of the real robot, and the pink is the planned position. And at such moments, like you see on the screen here, where the robot is about to grasp a timber strut, that's when the external tracking kicks in, and enables the robots to get to the right position in order to make sure that they form stable grips. So you might have noticed that in some of the previous videos, but you will notice that again here, that there's like some slight pause when the robots are about to open or close their grippers. What you might also notice in the video here is actually that there's this additional mechanism coming out of the top side of the robot. And this was an additional mechanism that we needed to integrate because for this assembly, after the previous videos that I showed, we upscaled the amount of timber struts that we looked at. And there was a lot of imprecisions in the milling of those timber struts because we use a local timber supplier in Stuttgart to do that. And then we had some tilting of the kinematic chains, which would cause collisions. So this mechanism was integrated in order to avoid that. What we additionally developed for this prototype was a screw driving effector that was based on an automatic feed screw gun, if you're familiar with it. And this allowed multiple screws to be held by the robot, and also for the robot to simultaneously drill 2 screws into the timber struts in order to make stable connections in between the timber and the plate below it. So this is what the final assembly looked like. It took about 17 hours, and the plate actually, to give you a bit of scale, measured 4 meters by 2.5 meters. and I did a bit of calculation. I think that's like 13 feet by 8 feet, so that's the scale of this thing. And the second prototype that we built, actually I just finished with my collaborator before I came to Cornell, so I only have this, although a lot of my slides seem a bit blurry, but this is even a bit more blurry. And hopefully by the end of my stay at Cornell, I can share some videos of the assembly process of that. And coming back to my interest in this team is actually, again, this exact question of architectural design. So more specifically on design methods and interfaces for designing and potentially rearranging the structures that we built. And this includes both top-down methods in which designers design blueprints for the robots to build, as well as more bottom-up methods where the design is emerging through the construction process and potentially derived from the intelligence of the robots themselves. More specifically, I'm creating agent-based models for collective robotic construction, which colleagues of mine actually at the ICD are exploring in other contexts, some of which you see on the slide here. So this includes the design and rearrangements of building elements in adaptive structures, the design of fabrication-informed timber shells, and the cyber-physical fabrication of fiber pavilions. And for those of you who might not be familiar, agent-based modeling is a computational approach that aims to understand systems through simulating at the agent level and the interactions of the agents in their environment. So to give you one example, this is like the classic example from agent-based modeling is the flocking of birds. And in agent-based modeling, instead of saying that we want to try to model the flock itself, we look at the birds and prescribe behavior, so some diagrammatic representations you see on the left, to the birds that would allow them to, in simulation, do patterns like you saw in the video. And this can be nicely translated to collective robotic construction in that we can look at agents being the robots, or potentially in some cases even the building material, and prescribe behaviors to those agents in order to derive structures that are informed by the assembly process or how they would be built by the robots in the system. And such models allow for the emergence of designs with varying degrees of architectural relevance that would otherwise be hard because there's so many elements or super tedious to design by hand. And what I've been exploring with the agent-based model is the relationship to other phases of typical construction processes. So the agent model doesn't necessarily only have to be utilized for design. If we start to combine the design and planning, this can give more agency to the architect, not only designing what is being made, but also actually curating how the process unfolds in real time, performing as a choreographer on top of a designer of a static object. So specifically me, who has training in architecture, I believe that the presence of a designer in collective robotic construction processes is important in the consideration of the development of such systems. And to better explain this, I jumped to the next project because I think it's because it was developed actually with the intention of making the methods that I developed for the previous project and for my PhD more accessible to students and people with no experience with collective robotic construction. And this was all originally done for a workshop that was held at the Digital Futures Conference in the summer of last year. And what we did was develop a fairly simple robotic system, which is called RADAR, and that stands for Roaming Autonomous Distributed Robot. And this is a two-wheeled robot that can navigate by driving around and has an electromagnet on the front, which allows it to grasp this digital material, as we call it, in the front, and move it around and form clusters in its environment. And together with that robot, we developed an agent model, which serves two purposes. The first is to be able to simulate how these robots interact with the material and each other in the digital space. And then also the model serves as a tool for deploying what we explore digitally into the real world. And this we did using ABXM, so a little bit of a plug here. The ABXM framework is a framework developed by the ICD and released on Food for Rhino and on the database of the University of Stuttgart some years ago. And what ABXM does is we hope that it's an open platform for experimentation with agent-based systems. The aim of the framework is to standardize research equipment with the hopes to increase transparency of agent-based models and the repeatability of research results. So what does that look like for the system that was developed? Well, for simulation, we have a mobile robot agent and a material agent. Each has unique behaviors, so the material has behaviors which allow or force the materials not to overlap with each other, representing physical properties of the material, and the mobile robot has behaviors that prescribe to how it would work and move around in the physical space. And this, as I said, can also be used with the physical system, again, using external tracking. So as a designer, the idea is that we can first work in simulation, design behaviors for the physical robot, see how that might work, and then deploy these behaviors with the real system, eventually even changing inputs to the behaviors to see how that would affect the physical interactions of the machines. And what this looks like is something like this. So what you see on the screen on the right is these little robots moving around, and the goal here in this video was that they would move the blocks, I believe, to this yellow area on the upper right side. And what we wanted to do in our workshop is knowing that this robot is kind of limited in its capabilities, we asked our students to reimagine what this robot could be or what this could stand for. And through the 7-day, very intense, we were calling it a hackathon experience, we started out with 4 or many hand sketches of what this could mean, and this eventually led into 4 more concrete concepts, which we called resource rush, light haul, collaborative carrying, and skyline scrubbers. And what was really interesting about the results or about each of these ideas is that the students, without any knowledge of collective robotic construction before, were able to touch on very poignant topics in the larger research field. So I will just quickly talk about each of the projects. The first one was a bit more of a game. So Resource Rush, the mobile robots were split into 2 teams, a red team and a blue team. And the goal was for the robots to bring as many of the digital materials back to their side of the environment. The important aspects that they were looking at were heterogeneity, so there was 2 teams, a red team and a blue team. Task allocation, so as you saw in one of the segments, within the team, there was robots that had different roles, and site organization, which okay, I didn't think I had sound in any of my videos. So you see the robot here actually was supposed to be a defender, so that was the role that it was prescribed, and it was supposed to be in this yellow area. First it wasn't, so it navigates into this yellow area and is contained in that region, and its role was to block the red team from going into the zone of into their zone and taking materials that they already collected. Lighthall merged the topics of lightweight construction and CRC. The idea here was to create dynamic and interactive environments that would adapt to humans. So the digital materials were adapted in two ways. First, they became these anchor points for this bending active vault. And second was that a human could grab a digital material, which was then utilized as input for the robots to determine if they should move the vault closer together or further apart to allow a person to walk in or eventually sit underneath. And this one questions notions of adaptability. I think I mentioned this early on in the lecture, where the robots could potentially, of such systems, CRC systems, could live in the structure and then change it as people are inhabiting it. The next one was called collaborative carrying, and this one took principles of nature, although the image is somehow on space. They combined a lot of ideas here, but the agents were seen as foragers collecting the digital materials to eventually build their home. And the other thing that they take from nature in this project, which you will see better on the screen here, is that they left traces in the environment so that the other robots actually know where they were and could use that in their decision making of where to go next. The other thing that I think is quite interesting in the video here is you see these two robots basically quote unquote collaborating. The assumption was that one robot wasn't strong enough to push the material on its own, so another one would have to go and help it to be able to push the block. And the last project was Skyline Scrubbers, which was a bit of an abstraction of the robotic system. The idea was that the robots could maybe also be drones, navigating a city landscape, and the digital material was actually air purifiers, so they were moving the air purifiers around in the city in order to purify the air. So Lighthall, Skyline, similar to Lighthall, deals with questions that relate to processes that are not just about the main construction of a building. So here maybe about maintenance or repair or other things outside just direct assembly. And after the workshop, we actually open sourced all of the stuff, so the robot and the agent model on Daros, which is the database from the University of Stuttgart, so it's available. And we've been slowly adding more of the behaviors that the students created in that workshop and also in the workshops that were to follow. What we've also been exploring in this is notions of centralization, using different types of perception. So you see on the far right, actually, there's now local sensors on the robots, so we don't have to rely on the external sensing. And what we've also been testing is different extremes of how different the behaviors of the robots are. So if one robot has some behaviors and other robots have completely different ones. And the last version of this, or the next version, actually, I'm super excited to join the Design Tech Studio and work with you guys in seeing what you can also come up with this platform. The next project I want to talk about is very much honing in on this notion, again, that the robots live and change, live in a structure and change the buildings that we inhabit. And this was also created for a Digital Futures workshop that I did with former colleagues Maria Jablonina and Nicholas Kubail. And here the proposed system is of mobile fabric sheets suspended from a false ceiling. The robot you might think looks familiar. Actually, this was a predecessor for the previous project and actually served as inspiration for the robotic development. But what you see, or what you will see, is that the robot is composed of two parts: an active part that's located above the ceiling that has the battery and brains of the robot moving it around, and a lower part that is connected via a magnet and holds the fabric and moves it around in space. And what we aim to do in the workshop is understand how different robot choreographies can affect the spatial qualities provided by the textiles. So the students were invited to develop their own choreographies using these kind of 3 steps that you see on the slide, somehow illustrated here. The first was just planning the robot actions in 2D. Second was then, with the tool that we provided, simulating and predicting approximately how the fabric would behave. And then finally, testing the said choreographies in the setup that we had at Tongji University in Shanghai. And the design and simulation was developed before the ABXM was released, but actually was a custom agent-based model that we gave to the students. But this model had very specifically 3 inputs: a target point, curve, or vector field that would prescribe to the decision-making that the robots had. And this agent-based tool was accompanied by spring-based simulation for the fabric that allowed for the immediate evaluation of the effects of a choreography. So in turn, general movement, transparency, overlap, and drapery of the fabrics can be looked at and studied. And then finally, the agent behaviors were then translated into robot control code and sent over to the robots. Here you can see the basic tests of one of our spinning in place choreographies, where the 2 robots carrying a single piece of fabric are traveling along these kind of different circular paths. On this slide, you see some of the results from the initial 2D planning of the movements of the robots. What started out with our students as fairly simple routines and quickly led into some very complex arrangements where the robots were doing totally random things to some things that were very controlled. And after a series of iterations of student proposals, we sort of realized pretty quickly that actually some very simple choreographies could lead to very exciting spatial results. So here you see one choreography with 4 robots, 2 pairs, each carrying a single sheet of fabric and moving along these different curves. Here there's 14 robots moving iteratively away and towards each other to create this corridor-like space. Here you can see the power of the robots actually just following straight lines, and due to different timing of the movements of the robots along those lines, you can create different patterns, and then a large group of robots following elliptical paths. On this slide, now we see all 3 steps of the process. A team of 3 robots is holding 3 pieces of fabric. Each moves along straight lines in order to mobilize the fabrics. And a second one where 3 machines each carry a single piece of fabric and are moving along circular curves. And what is shown in this project is the possibility, again, of embedding the mobile robots into architectural building systems. We can design CRC systems that not only assemble the structures, but also change them in their operational phase. And what you see in the video actually is that the environment and people actually have a huge impact on how the textiles act. And although we were actually, in this project, not able to deal with such factors in the development, a recent master students of mine, Yagmor, Paula, and Galero, who just presented their thesis also before I came to Ithaca, recently developed a distributed system that attempts to address the human presence in the space and what their desires might be. So although the machines in this project are not mobile, they're distributed throughout the space, and it's only through their collective action that they can change the spatial quality of the fabrics that they control. The fabric, together with the motors, not only create and define the space, but also serve as a physical sensor to understand the human presence. So what does that actually mean? Well, fiducial markers were embedded into the corner of the fabric and served as a means to analyze engagement with the physical system. along with physical touch, actually, which can be monitored by the sensors in the motor, in the motors that actuate the physical system. And these things can be used, or those sensory methods can be used to propagate a digital representation of the physical system, which then attempts to change the choreography of the motors in order to achieve different moods and spatial conditions in the space. With the ultimate goal of spaces being able to change based on not only based on the level of the building system, which we see a lot with smart homes, but also make spatial change based on conversation and interactions with humans. And the last project I want to talk about is also from master's students of mine, which come from the iTech Master's Program at the University of Stuttgart, and this project was conducted by Nicholas and Greg. And the aim of this project was to present a novel approach to designing autonomous construction systems by teaching the robots how to act relative to the way the material behaves, and then using this relationship in between robot and material as a driver for design and assembly. The case study that was chosen was to make a structure out of bamboo bundles. So the animation that you see on the side is a rough idea of how that assembly process would work. And the robot has 5 degrees of freedom and a variable diameter claw gripper, which would allow it to swing on bamboo bundles, grasp bundles of different size, and navigate the structure. And what is interesting about construction with bamboo is that certain aspects of the assembly process can be very easily predicted, and therefore the robotic actions can be hard-coded in order to achieve certain goals. So like the thing that you see here, just navigating along the bamboo element and reaching this other element at the very end. Or here you see like a robot just swinging around on static bamboo, picking some bamboo up and moving it to somewhere else on the structure. But when active bending of the bundles occur, programming the robotic actions to achieve this becomes a much more difficult task, because there's some heterogeneity of the building material, so predicting actually how it will behave becomes a lot more difficult. Therefore, a machine learning model, specifically reinforcement learning, was used to teach the robots how to swing and bend bundles by operating relative to the bamboo's bending behavior. And the knowledge gained from the machine learning process is twofold. First, the robot uses or learns in digital environment how to use its weight and momentum to be able to bend the bamboo to a desired location, which can be used in the physical deployment of the robot. And second, actually, the robot learns how to determine what the material is capable of, which then might be useful in designing the structures that would be built by such a system. So the design and assembly processes are therefore driven by the relationship in between the robot and material. Design and assembly can be integrated into an iterative process where you navigate in between the simulation and the corresponding choreographies of the robots in this iterative process. And as such, materials actually not only serve as a passive element that can be utilized in construction, but also an active driver for the design and construction process. So to wrap up and zooming a little bit back out, collective robotic construction is one of the many approaches to construction automation. Each approach provides a unique opportunity for the creation of safer, more efficient, and sustainable construction. Some of these approaches, like the ones you see here, are already quite advanced and slowly being integrated into practice, leading to higher levels of productivity. But collective robotic construction still needs further research in order to continue to be proven viable. And this I hope to be chipping away at with my research. So my dream actually is to have a construction paradigm where real architectural structures can be robotically built or changed adaptively with teams of small machines. And before I end my lecture, I just want to say like a lot of the work that I presented is actually through amazing collaborations that I had with different researchers, professors, and students. This is a photo from the very early days of the NCDC. And with that, I would just say thanks. Thanks to everyone here for listening, and of course to the people who are also online. And I don't know if there's time, but maybe I can also answer some questions as well.
Hey, Sam, thank you so much. Is there a reason that the agents, like in the first project, can't coordinate in triads, like 3 of them?
Yeah, so we did actually in the very early stages of the project an analysis of the or like how different kinematic chains, these topologies of how the robots and building material connect to each other, how that relates to the payload of what the robot would actually have to be able to carry, as well as what that means for what types of things that it can build and can be designed. And the reason why it's only this 2 robot system is actually because we kind of realized that at the very beginning we could still assemble structures with such a simple topology. And now, actually, as we further develop the system, we're opening up this actually a little bit more. The robots actually have 2, maybe 3 degrees of freedom. But what becomes super tricky also with more robots interacting with each other is actually forming stiff enough connections in between the elements that the body of this like kinematic chain is stiff enough and therefore precise enough to do the assembly task that we want it to do. Whoops.
Thank you so much for your wonderful lecture. I think in the first project that you presented, you mentioned that the robots were reacting to wood struts, and there was a digital twin to help facilitate that interaction. And then as you continued, I really liked at some point, I think with the current project that you mentioned, that there was a digital representation of the physical environment. So for me, I was wondering if you could answer maybe even in general terms, like when do you choose to simulate the physical environment through digital twin versus digital representation that's related to the physical?
Yeah, it's an interesting question. I think in the second project, actually, we tried to, in the various iterations, actually determine which of those strategies is actually best. And I don't necessarily think I can answer that question, right? I think it's very project specific, whether or not we've gone for modeling exactly the system as closely as we can, or actually trying to embed information that we collect from the physical environment. But I think the general approach that we try to now shift towards is to embed as much local sensing that we can on the robots themselves and move away from this external tracking for the purposes of trying to fulfill this like visionary image of what collective robotic construction means, in that their mobile nature, right, means that they could go in crazy dimensions. And with external tracking, then you kind of decrease, right, the range at which they can operate.
Hi. So I had a couple of ideas. I mean, one was, could you do the flocking thing with your hanging curtains? Because that would allow you to have sort of like a time trace in some sense, like the bottom of the curtain tells you where the robot was, and the top of the curtain tells you where the robot is. And so you get some sort of three-dimensional flocking behavior. So that's one idea. But the question that I have is, so one of the things about making this viable is trying to figure out where you do better, or where you will eventually do better than people as workers, right? So, if it takes you, if eventually you'll be able to make a structure, on the same time frame as human beings, then maybe you can argue that this is the way to do it. So the first place where I saw it was when you were making more random sort of patterns that you couldn't really, like a human would have to measure, and it would be tough, and figuring out like the loading and all of that would be difficult. So I think that was one place where I saw it, obviously, but I was wondering where you, like where are the places where you see these robots doing better than people in the long run?
Well, actually, like with the first system, we did actually at some point an analysis of the assembly process as compared to some other types of automation systems that are doing fairly similar automation processes. And you're right, like I think you noticed in some of the videos that it's like 50 times faster, because actually the robots are highly geared to give them enough strength in order to be able to do some of do this lifting of the other robot. And so when you compare it based on time, they don't perform super well, but in other aspects, like I somehow mentioned in the very beginning, like this comparison of the size of the robot relative to the structure that it builds and cost, actually they do perform fairly well. And so in that sense, I guess there's a bit of maybe a trade-off that can be thought about when like if you have certain constraints, what that might be, or like if these types of systems might be better. I mean, but a big conversation that we started to have in Stuttgart about these types of systems is also to construct building systems that would otherwise be in areas that are hard for humans to work in. So the example that I have for that is we just had a student group that I mentored that made this kind of worm robot that was like 3D printing around its body and like traveling through the tube that it was creating. And they will continue to work on this, and there's a lot of discussion and thoughts about, okay, piping or conduits in wall spaces where in renovations or maybe also in new buildings where, again, like humans might not be so comfortable or easy to get to.
Thank you, Samuel, for really, really excellent lecture. Maybe building on some of those topics related to labor and collective intelligence. I'm curious if you have brought on collaborators from the building trades, you know, framers, builders, that have a body of knowledge and years of experience that could potentially inform the, you know, the next steps of where you take this and maybe address some of Itai's questions.
It's an interesting question. Well, the short answer actually is we haven't really done this so much. At the NCDC, we have some like industrial partners with some timber manufacturers, and we've shown them the project, and they seem interested in it. So maybe you're right that there's some further kind of conversations and discussions that should happen there. But yeah, for now, haven't really done that. I think in the US, what it would be even more, or potentially even more interesting for these like smaller homes where we see a lot of this kind of linear element timber construction happening.
Thank you.
Yeah, thank you for sharing of your great work. And I have some questions. Just maybe I didn't get some, so I just some question about that. I feel like the second and the third one is like moving from the plan, and I think you mentioned that the second one maybe in the future can be used on by the drone with some air purifier, right? So I think about this from the plan to a more three-dimensional way. So it's a more practically thinking that be used in the real world. And I have a question about the robotic one, about the collective construction. Like you said, maybe hopefully can like we just mentioned, the advantage of it is smaller and it can be easily more maybe applied on different layers that human not that easy to achieve. And I feel the fourth one maybe smart is it has a joint itself, so it can move from the ground to the upper layer. I'm curious about the first one is whether there are some ideas about moving from the floor to another layer, so can like build with a higher building or construction, because I find in some diagram it showed it can move in or from horizontal or vertical or different floors. I just wondering whether how it can be applied that from a lower point to a higher point. Is it can like create a joint and lift from one to another so it can create a more 3D structure? I'm just curious about that, whether that is solvable or have some ideas about that. Yeah.
Yeah, so with the first one, this thing that I talked about that was coming off the side of the robot, we actually further developed, which allows the kinematic chain to actually tilt in other directions. So if the first one tilts the robot up and the second one actually tilts to the side, then we can actually build in 3 dimensions. Or we can just like step up layers and build on top of the layer that's already being built. So yeah, there's already some work done. Like I showed one image of it, but hopefully, like I said, maybe you can stop by the office at some point later in the semester and I can show some videos from that. And yeah, the second one, I think the idea there is actually rather to be like a educational tool, learning about concepts of collective robotic construction. I think actually the concepts from there can be translated very easily to drone systems or systems that work in 3 dimensions. So it's for sure possible. I think it's supposed to be actually utilized that robotic system in a way of exactly questioning what we can do or what the material or the robot can be, and as a starting point for developing systems with different capabilities. is there something online maybe? Oh. Ah, okay. Yeah.
Hi, thank you again for the lecture. So I myself am not an architect, but I am kind of getting myself familiar in that space. And I do know within construction, there's this process of normalizing sites to make them more efficient and better for organizing, human labor. I wonder if there's a similar kind of dynamic or process for normalizing sites for collective robotic construction.
Yeah. Again, coming back to this dream, I think one of the dreams in the community of collective robotic construction is like at a very long shot, like space, or also deploying these systems in hazardous areas for people to build shelter that maybe eventually people could go into. But I think like research so far on these systems is very much in most senses in laboratory environments. And I would definitely agree that some sort of preparation would need to happen for any of these types of systems, mine or the work of others, in order for them to be able to function. There was a researcher at the ICD before me. His name is Nathan Millenbrink, who's now teaching at MIT, who did a collective robotic construction system that was actually doing pile driving, so actually driving metal sheets into the ground to change the way that I think actually erosion was happening of the earth that was on different sites. So I think actually there would be potential for even thinking about a collective system that could do this site preparation thing. But yeah, no, 100%, all of these things would need some sort of setup in order to start going.
For those of you online, remind everyone that next Tuesday we have another lecture in the series. Same time. Location will be in Goldsmith Hall, and Banaz Farahi will be joining us from the MIT Media Lab. So please come back for that lecture. Thanks again, Samuel, for an excellent talk.